Alright, so this video is going to be about energy diagrams and interpreting them and what they mean. And I'm going to show you an exothermic example and an endothermic example. So let's look at the exothermic example first. We have this reaction, A and B produce C and D. So A and B are my reactants, C and D are my products. When I look at this energy diagram, what this does is it shows me the energy over time during my reaction. And we can think of this y-axis as energy, so if it's higher up, it's got higher energy, lower down, it's lower energy. And my x-axis is the reaction progress. So over on the left is at the beginning of the reaction, to the right, that's at the end of the reaction. So it's what's happening to the energy over time as my reaction proceeds. Notice some things to notice in these energy diagrams is my energy will always go up a little bit before it goes down, and my products can either be lower than my reactants in this case, or they can be higher than my reactants. In this example, in an exothermic reaction, my products are lower in energy than my reactants. So since my products have less energy than I started with, that means some energy must have been lost during this reaction. If energy is lost from the reaction, that means it's giving off energy to the surroundings, meaning this reaction is exothermic. If you were to feel this reaction with your hands, it would feel hot to the touch because it would be giving off heat energy to your hands. If you were to calculate the heat of reaction, that is the energy of your products minus the energy of your reactants. So since my products are lower than my reactants, my heat of reaction is negative. So we are going down to get from reactants to products. The other important value in here, apart from the heat of reaction, is something we call the activation energy. The activation energy is the difference in energy between your reactants and what we call the transition state. That's that peak there in the middle. And what this represents is the energy required to start a reaction. So even if a reaction overall is exothermic, and an example of that would be, the combustion of methane. We did that in class. That is a very exothermic reaction that creates flame and heat. But in order to get the reaction started, you're going to need to input energy by lighting it with a lighter. So that lighter represents the activation energy, that initial energy input required to get the reaction started. And that activation energy corresponds to the energy needed to break the bonds that you initially have in your reactants. So before we can form products, we first have to break apart the bonds in the reactants. And since your atoms and your molecules, they're attracted together by those bonds, in order to pull those atoms apart and break those bonds, that requires an input of energy. So that's going to be a positive value. When you form new bonds, that will release energy. So the second part here that goes down corresponds to the energy released from making those new bonds in the products. So this energy is breaking the bonds in the reactants. This energy is making those new bonds in the products. And in this case, I release more energy from making the bonds than I used up in breaking my initial bonds. So overall, there is a net loss in energy, and we say it is exothermic. Okay. Over here on the right, this is an endothermic reaction. You'll notice I drew the reaction. This is the exact opposite of this reaction right here. So if I were to compare their heat of reaction values, they would be the same value. Like if this was negative 200, this one would also be 200, except it would be positive 200, because in this case my products are higher in energy than my reactants. So I gained energy over time. So we say it's endothermic because it's taking in energy. And some things to notice again about this graph is it always goes up before it goes down. You will always see that in an energy diagram. That initial part that it goes up is known as your activation energy. Okay, and that's also the energy required to break your initial bonds. The amount that it goes down by, that is the energy that's released from making new bonds. And then the difference between that is the heat of reaction. So the heat of reaction is comparing the energy of your products to the energy of your reactants. So it's the distance between these two lines right here. And in this case, since my products are higher than my reactants, my heat of reaction is positive. Again, it's an endothermic reaction. So this reaction would feel cold to the touch if you touched it, because it would be absorbing heat energy from the surroundings. And if something absorbs heat from you, it will feel cold to you. And again, notice this one, other thing to point out, this one has a very large activation energy, so it's going to require a lot of energy to get this reaction started. So it's probably a lot less likely that this reaction would occur in nature because it was going to take a lot of energy to make it happen. So less likely for it to occur in nature.